Hello everyone, this is Dilip. When we are talking about neural networks in the previous videos, I missed talking about an important concept called activation functions. We look at it in today's video. So this is a simple neural network we'll take for example. We'll see what is the need for activation functions. Where we'll apply it, we'll see in the later slide. But what is the need for activation function? So if we take a simple neural network like this shown in the picture or any complex neural network, we will find it ultimately it is like a linear function. So if we take the hypothesis at this point, it is nothing but it is a sum of weights multiplied by whatever the values we are getting it here. And as you can see, it looks like a linear function. And if we just move ahead and say what this neuron is getting its values from, it is also summation of weights multiplied by the input features. So this is also a linear function. Now, if you put this over here, A11, if you replace by this equation, it might look like nonlinear, but it is not a proper nonlinear one. So if we want to have more nonlinearity in our neural network, such that for a given nonlinear problem, it can compute nonlinear complex features such that our results will be much better, then we have to rely on activation functions. So these activation functions, what they do is they will take a linear input and they will convert it into nonlinear input. So that is the goal for us in order to use the activation functions. And where do we use the activation function? So within each neuron, whenever we compute the summation of weights multiplied by the input features, after that we will take this as input and we will activate it by putting it into a nonlinear function such that we get a nonlinear output. And the reason for going this way is because the inputs are also nonlinear. For example, if you have two features, then it's a linear problem. You can represent it in XY axis. But if you have more than two features, then it's a nonlinear problem. So for that, if you go with nonlinear activation functions, our neural network will become more complex and it will give us better result. And for analogy, let's look at neurons in our body. So whatever the inputs it gets in the form of electric signals from other neurons, what it does is it will take the input and it will do something to the input within this cell body. So it is doing some activation such that whatever the input we get, it won't be the same input, but it does some modification. So, and then it sends to the another neuron. In the similar manner, whatever neuron we have in the neural network, whatever the input we get, we do some activation to it in the end, and then pass it on to the next neuron, such that it becomes a nonlinear one. And this is one of the nonlinear functions which you've already seen, which you are using in logistic regression for binary classification. Even for non-binary classification, we are using the sigmoid function. So the sigmoid function, what it does, it takes the input and it makes sure the output will be between 0 and 1. And if the input is less than 0, it will give 0 as a result. If input is greater than or equal to 0, it will give 1 as a result, because it will output any value begin greater than 0.5, we take it as 1. Any value less than 0.5, we take it as 0. So for binary classification, we do like that. So this is the function to output. So whatever the input we get, we calculate 1 by 1 plus e to the power of minus that input to get the output. This is a sigmoid function. Now, the sigmoid function, we can't use the activation function in neural network because this has the problem of vanishing gradients. So why do we get this vanishing gradients? Before that, the sigmoid function output is always situated between 0 and 1. So it will be like 0.1 or 0.2, 0.5 or something. It's always its value will be that. Now, once we have a more complex neural network, what happens is we keep multiplying these gradients. So it becomes like 0.5 into 0.5, 0.5 into 0.5. So that value will keep going down. So that way, at some point of time, if we take a complex neural network, the input layers will have no input being given in the end. Once we go for backpropagation, we will come to know that our gradients, which are computed on the input layers, they will become useless. So that's the reason we avoid sigmoid function for as activation function for neural networks. Then what is the solution? We go for rectified linear function. So here what happens is, this is the simplest to implement as well. So whatever the input we get, if it's a positive value, we directly output it as its value. And if its value is negative or 0, we give it as 0. So it's simple implementation as well. So you just output max of 0, that value. So for negative values or 0, it gives 0. For positive values, it gives that outputs that value. And there are other variants of rectified linear functions, which you can study online. But this is the most widely used activation function in neural network. Now, there is some problem with this ReLU as well, where for negative values, it doesn't give anything. So the neurons can become, which are outputting negative values, can become zeros, and they don't contribute in the neural network. So for that, there are some more improvements which you can study online. And another important activation function will be used in neural networks is Softmax. So this will only be used in the output layer of the neural network. Now all the previous activation functions I discussed, these are independent. So they are only dependent on the neuron input. But for a Softmax, it depends on the inputs of all the neurons together. So it's a more generalized form of sigmoid. It also gives between 0 and 1. What it does is it takes the exponent of the input value and then divides with summation of all input values. This way, this will make sure its value will be between 0 and 1, as well as it will give us a better output for classifying problems. I'll give you a simple example. Say if you have a simple neural network looks like this. So one of the values after you apply Softmax to this last layer will be 0.7, 0.2, 0.1. If you summate them, it will be equal to 1. That is what we want. The output layer, the probability together should give us value of 1. And since the value is highest on the 0.7 on the first one, this output indicates it belongs to class 1. Here, the output is highest in last neuron. So it means it belongs to class 3. So that is the use of Softmax. So in Softmax, we only use in the output layer. In between hidden layers, we rely on ReLU. So that's it about the activation functions. In the next video, we'll look at a practical example of using these activation functions and neural networks for classification problem. Thanks everyone for watching the video. Bye.